I'm Mark Renes, and this is Euler's Melting Pot. In this challenge, we try to complete every Project Euler problem in a different programming language. Today's challenge is problem number 8. Find the largest product of 13 adjacent digits in this excessively large number. This is a 1,000-digit number, and we'd like to look at subsequences of length 13. That is to say, there are 988 possible subsequences we need to consider. Today, we'll write our draft in Ruby. Let's write a function to return all of the subsequences, or sliding windows, of a given length in a string. In our case, we'll use this function on our 1,000-digit string and ask for windows of length 13. But let's write it in full generality. We accumulate an array. To do so, we iterate from 0 up to and including the start of the final window, which is equal to the length of the input string minus the window size. At each step, we take a substring from position I up to I plus window size, this time excluding the upper bound. We store that substring in a result array, and at the end of the loop, we return the array. As a reminder, in Ruby, the last expression of a function is returned, so there's no need to explicitly write the return keyword unless you want to exit a function early. The each method is the most general purpose way to iterate over an enumerable data structure in Ruby, such as a range. Given a block, each will call the block for each element of the data structure. Ruby provides two range operators, which differ subtly, and we've used both in this example program. When two numbers are separated by a pair of dots, this indicates an inclusive range. So 0.5 would return a range representing the numbers 0, 1, 2, 3, 4, and 5. On the other hand, when two numbers are separated by a triple of dots, this indicates a half-open range. So similarly, 0.5 would return a range representing the numbers 0, 1, 2, 3, and 4, excluding the upper bound of 5. Now we have our array of values. As we've discussed before, Ruby puts an emphasis on stream-oriented functions. So rather than writing a traditional for or while loop to do our work on this array, we'll use the facilities provided by the enumerable interface. First, let's write a function that, given a string of digits, returns the product of those digits. As mentioned previously, the module enumerable is the central interface for objects in Ruby which can be iterated over in some form or another. Classes like array and hash fit under this umbrella, as both can be iterated over in some well-defined way. Strings, incidentally, do not fall into this category for a very good reason. Strings in Ruby can be stored in different encodings, and depending on this encoding, a single character might be stored as multiple bytes. For instance, the character 7 at the start of our string corresponds to the ASCII value 55. In the ASCII encoding, it would be stored as a single byte 55. In the commonly used UTF-8 encoding, which is compatible with ASCII, it would be stored the same way. However, in UTF-16, it would be stored as 2 bytes, the first of which is 0, and the second of which is 0 hex 37. All this is to say that the phrase iterate over this string is an exceedingly ambiguous instruction. Depending on our needs, we might wish to iterate over each Unicode character, each code point, each individual byte, or even each line of the file. Thus, Ruby forces us to indicate our intention, providing not 1, not 2, but 5 different enumerable-like each methods. Now, in our case, all of our characters are standard ASCII digits, and string literals in Ruby are encoded in UTF-8 by default, so each char will suit our needs nicely. Each char is similar to each on enumerables, in that it can be used as a sort of for loop. If given a block, it will call the block for each character in our string. However, each char, and all of the other enumerable functions in Ruby have another capability. If we omit the block and simply call each char with no arguments, it will return an enumerator object over the characters. Effectively, it returns an array-like object that we can call other enumerable functions like map on. Here, we do just that. We call each char without a block to get an enumerator over the characters of a string. Then we call map on it, which applies the block to each element of the enumerable, and returns another enumerable of the results. For our map call, we want to parse each character as a number. So the character 7 with ASCII value 55 should get converted into the number 7. This conversion is done with the Ruby method toI, which stands for toInteger. At this point, we have an enumerable, an array in our case, of integers, and we want to multiply them together. Specifically, we want to take all of our array elements and multiply them one by one to accumulate a final result. If you watched the very first video in this series, you might recognize this as a fold operation. We want to take a binary operator, the multiplication operator in this case, and fold it over a list to get the total product. In Ruby, the fold operation is implemented by a method called reduce on the enumerable module. It takes a block indicating how to combine the elements of the array. Once we have this function, we want to apply it to each of the subsequences we found earlier. We have a list of the subsequences, so we'll use map on that to get our result. Now we have a function that produces a list of products. We want the maximum element of this list. Ruby makes this incredibly easy, providing a function called max on the enumerable module. This is a working program, and it's about as efficient as it's going to get, all things considered. We can, however, make some minor stylistic improvements. First, we can take our map call in digit product and convert it to this. Let's see why this is. A lot of modern programming languages support two types of arguments: positional and named. For instance, in Python, unless you go out of your way, any argument to a function can be passed either as a single value or associated to its parameter name. The benefit to named arguments is that an argument can be self-documenting. Compare these two function calls. One of these is much more clear at a glance than the other. In Ruby, on the other hand, an argument is always either positional or named, not both. Every argument we've worked with so far in this program has been exclusively positional, and an argument can be followed by a colon to indicate that it must be passed by name. This is what the play sound example would look like in Ruby. Further, in Ruby, there aren't just two kinds of arguments, but three. An argument can be positional, can be named, or can be the special block argument. That is, the most general possible function signature in Ruby is this, where any positional arguments will get collected into the args variable, any named arguments will get collected into the quargs variable, and a block argument, if present, will get collected into the block variable. The block argument is particularly special. If a function takes a block argument, we can pass it in one of three ways. First, we can use a pair of curly braces. Alternatively, we could use the keywords do and end to delimit the block. This is equivalent to curly braces except that it carries a different operator precedence. Finally, we can pass a value, such as a local variable, as the block argument by preceding it with an ampersand. More on that in a moment. More concretely, here are three different ways of mapping the absolute value function over a list, using each of the three forms we discussed. In Ruby, absolute value is a method defined on the number object called abs. Note that if I want to use the do-end form, I need extra parentheses around the puts call. Without them, the block will be interpreted as an argument to puts, not to map like we intend. In the third form, we create a procedure object, which is capable of calculating the absolute value of a number. Internally, this is really just an object like any other, except that it happens to have a method called call, which will execute the block. To pass this object as the block argument, we mark it with an ampersand. Now there's one other little trick we can use. If we try to pass an object that isn't a procedure object as a block argument with an ampersand, then Ruby will call the method toProc on it to convert it to a procedure object first. This works on any object which defines a method with the name toProc. So if we were feeling particularly loquacious, we could take the absolute value of our list like so. This may not look helpful, but several built-in Ruby types define a toProc method as well, one of them being the symbol type. A symbol in Ruby is sort of like a string, but it's guaranteed to be interned in a global hash table. This allows symbols to have constant time equality comparisons at the cost of not being easily modifiable. The toProc method on a symbol converts the symbol to a procedure object. Specifically, the resulting procedure calls a method matching the symbol's name on the block's first argument. That is, it literally converts a method call of this form to one that looks like this. So our map call can actually be shortened to this. Now, let's apply that back to our original program. toI is just a method on an object, so we can use a symbol literal as our block argument. Likewise, multiplication is actually just a call to the method called star. So in both of our cases, we can shorten the block argument to a symbol literal. Now you may be thinking that this is the point in this video where we reduce this program down to while loops, gotos, and eliminate any form of abstraction. But we're actually not going to do that this time. This is IO, a pure object-oriented programming language heavily inspired by Smalltalk. Specifically, IO is a prototype-oriented programming language, in contrast to most other current object-oriented languages, which are based on the notion of classes. In a prototype-oriented language, there is no distinction between the class of an object and its instances. There's only one sort of thing called an object, and objects inherit directly from other objects. To see the difference, let's write a short Ruby example using the more conventional class-based approach, and then we'll see how it translates into the prototype-oriented language we'll use today. We might go back to a first-year programming course and elect to write a class called Animal. For our purposes, animals are capable of exactly one thing, making sounds. For our parent class, we don't know what kind of animal we are, so we'll just assume the default sound of an animal is, naturally, hello. Once we've done that, we can write some subclasses. Subclasses inherit the behavior of their parent, and indeed, are subtypes in the mathematical sense. That is, our subclass cat has the property that every instance of cat is also an instance of the animal class. This doesn't come up as often in a dynamically typed language like Ruby, but this property is indispensable in a statically typed object-oriented language such as Java or C++. For this example, we'll define two classes, cat and dog. Finally, we've defined a bunch of classes. It's important to note that we have no instances of these classes yet. That is, it's not reasonable to say that we've created any cats or dogs yet. All we've done is indicate what a hypothetical such animal might look like in the future. Now we can create instances using the constructor. In Ruby, we invoke constructors using the method called new on a class. Now my cat is an instance of the class called cat, and we can ask my cat to make a sound, at which point, of course, it will meow. To be clear, we started by defining what our objects were meant to look like, and then only once we had determined the shape did we actually begin to construct instances. The shape in Ruby, and in most class-based languages, is strictly separated from the instances proper. Now, let's do the same thing in IO. IO doesn't have classes, so we can't have an animal class that describes the shape of an animal in the abstract. Instead, we're going to create a single object, an instance, which will stand in as an example of an animal. Then, when we want to create new animals, we can tell IO to use the existing one as an example, and then change the bits and pieces we want changed. First, we construct an animal. Every instance must use some other instance as its prototype, to indicate what its behavior should start off looking like. So our animal will be based off of the original instance called object. Then we define a method on our animal object. Note that, although I've capitalized this variable's name, it really is just a variable containing an object like any other. Animal, in this example, is not some abstract hypothetical. It's a perfectly valid example of an animal in its own right, and we could call make sound on it right now. Now, we define two further refinements of the animal object. We do so by using animal as an example and cloning it. Then we refine the make sound method in each child. Now, we have a cat. In fact, we have the canonical example of a cat, called, fittingly, cat. This canonical example is perfectly capable of making a sound. We can also construct more examples of cats by cloning our canonical example and having those cats make sounds. There are a few things to note here. First, the method to make a new example from an instance is called clone. If you're coming from a Rust or Java background, you may be imagining clone as some sort of deep copy operation that constructs a new object that superficially behaves like the original. That approach would be called concatenative prototyping, where a new clone of the object only bears resemblance to the original, but does not remember its own parent. IO, on the other hand, follows the model of delegating prototyping, where an object's clone remembers who it came from and will, upon encountering an unknown situation, refer back to its linked parent. To see the difference, suppose we realized halfway through a program that the shipping company messed up our order. Rather than sending us demure house cats, they accidentally sent us a box full of lions. If we go back and change the make sound method on cat to sound a bit more like a lion, then all existing cats which were cloned from this canonical cat will be updated to reflect this change in behavior. In a prototyping language using the concatenative model, this change wouldn't propagate to cats that we had already constructed. This sort of approach to programming is very dynamic and is conducive to rapid prototyping. As requirements change, so do the nature of the objects we're studying, and IO is readily equipped to handle those changes live. You may be wondering, if every object has to have a parent that it was cloned from, then what is the parent of the original instance called object? In IO, we can use the proto method to get the prototype or parent of an object. As it turns out, the parent of the canonical object is another special object called lobby. Lobby is the global scope of your IO program, so any variables defined in the top level are available in lobby, therefore in its child object, and by extension in every IO object. Lobby has a parent too, and it's called Protos. Protos manages the core IO implementation as well as any add-ons that have been loaded. The parent of Protos is core, the IO implementation itself. This is where built-in objects like string and list are defined originally. Finally, the parent of core is object. All of this bootstrapping is done during startup at a very low level, making object its own great-great-grandfather. We'll be working with lists in our final program, So let's take a look at how to work with lists in IO. Let's construct an example list and try to map the absolute value function over it, just like we did in Ruby. In IO, lists are constructed using the list method. List is not a language keyword. Most things in IO, including list, are simply methods on an appropriate object. This also includes things like if, for, and while, which are not language keywords, but are simply methods defined on the canonical object, called object. If we try to use square brackets to define a list in IO, we get a rather provocative error message indicating that a method called, literally, square brackets has not been defined. In fact, when we enclose values in square brackets in IO, we're simply calling the method called square brackets on the current local scope. This method is not by default defined, but we're free to define the behavior to do whatever we wish. In our case, let's define square brackets to return a list. Now, similar to Ruby, IO has a sort of special way to pass blocks of code to methods. To be clear, this is not some exclusive syntax baked into IO. We are taking the local variable, myList, and calling the method map on it. We're passing two arguments to map. The first argument is x, and the second is x_apps. You may be thinking, what is x? And that's a fair question. There's no local variable or method called x in the code we've written. So if this method evaluates its arguments, then it should produce an error indicating that x does not exist. However, this method does not evaluate its arguments. IO puts a huge emphasis on reflection and introspection capabilities. So while the default behavior of a method is to evaluate all of its formal parameters, a method is free to declare no formal parameters and do whatever it pleases with its arguments instead. We'll see an example of that in just a moment. This call, despite its unique evaluation semantics, behaves like we would expect. For each element of the list, we assign a local variable x to that element, and then we call x_abs, returning a list of the results. Similar to Ruby, we can actually shorten this one more. If map is given just one argument, it assumes the argument is the name of a method to call on each object, similar to passing a symbol as a block argument in Ruby. Let's write some functions of our own. There are two ways to define functions in IO: method and block. Method defines a new method, which binds itself to an object and automatically evaluates when mentioned. Block defines a more standalone function, which captures the local environment and only evaluates when explicitly called. Here are two functions to square a number in IO, one written as a block and the other written as a method. To call a block, we have to invoke it using the call method on the block itself, passing the arguments to that method. To call a method, we simply mention its name, followed by some arguments. If we want to get the method object itself without calling it, we can use getSlot, which bypasses method evaluation and returns the underlying object that we can then call later. Let's write a method that behaves like map. For the sake of simplicity, we'll focus on the variant of map that takes two arguments, a variable name and a block, rather than implementing all three overloads. We'll call our custom method myMap, and we'll define it directly on the built-in list type so that it can be called from any list in IO. First, we'll need somewhere to put our result, so we define a result list that's initially empty. Now, previously when we defined our square function, we told method that it was to receive an explicit argument. This enables the default and most common behavior, which evaluates the argument and binds it to a name. But in our case, we don't want to evaluate the arguments. We want to set up a custom context and do something unique. So our method is actually declared to take 0 formal parameters. To get the arguments, we use the call object, which supplies us with information about the current function call that's happening right now, including all of the arguments, who called it, and what the name of the method was. We get the two arguments from the call. The first one is the argument name, and the second is the body. Each of the arguments is a message object, which is a block of code with no context associated to it. For the second argument, that's exactly what we want, as we'll supply the context ourselves in a moment. For the first, we expect the name of a variable, so we get the message's name field. Now, I said that a message object is a snippet of code with no context. That means we need to supply the context ourselves. A block's context indicates what local variables and methods are available to the block's body. If we want this block to behave intuitively, it should be able to use local variables from its enclosing scope. So we're going to take the caller's context and clone it to create a new context that inherits all of the local variables from the caller. Now, we start a for loop. This behaves about like you might expect. We're going to run the loop body several times, with I ranging from 0 up to the size of the list minus 1, inclusive. We never defined a variable called size, but we don't need to because we're in a method on the list object, and a list always knows its own size. Inside the loop, we get the relevant value from the list. Then we bind it in our local context to the argument name so that the body supplied by the caller can access it. Once the context is set up, we run the message called body, which the caller supplied, in the context we've just created. This executes the body with the local variables taken from our context object. That includes any local variables inherited from the caller scope, as well as the new variable we just assigned. Finally, we push our new value onto the end of the result list. At the end of our loop, we return the result list. Just like in Ruby, the final expression of a method or block in I/O is returned implicitly. Now, let's start writing our actual solution. First, we define our total variable, just like in Ruby. Then we define our current position variable to keep track of where we are in our string. We iterate 988 times to get all of our windows. We're going to map over this range to get all the products. To get the substring, we use xSlice, which stands for exclusive slice. Increment our position variable, then we calculate the product. To calculate the product, we iterate over the range from 0 up to and including 12. For each index, we get a character from our string and convert it to a number. Then we reduce all of the numbers by taking a product, again, just like in Ruby. Like map, the reduce call can take a couple of different forms. One that takes explicit arguments, and one that simply calls the method with the given name. In our case, we simply want to call the multiplication operator, so we'll use the most compact form. At this point, we have a list of values, and we want the maximum. We perform another reduce operation, this time using the max method to get the largest value. We convert that value to a string and then print it out. And this gives us the solution to Project Euler problem number 8 in I. Tune in next time when we tackle the 9th problem in the Shakespeare programming language.